So in this lecture, we are going to talk about the capstone project that we will be doing. The requirements are as follows at an abstract level. Um, so we are going to build a Q&A system. It's going to respond to a user's request in terms of natural language and provide an answer. In some sense, you can see this as an analogous to providing a natural language interface to and underneath a database. The difference being the database is not is unstructured. It doesn't contain any schema. For example, you might have a weather bot and that then tracks with an API provided by, let's say, Yahoo Weather, where the parameters are basically known beforehand. So in that sense, you can think of the Q&A session as responding to user queries and resolve the queries against a set of a Wikipedia documents, basically text. So then how do we design such systems? Now, what are various components are required to accomplish this task? Just as the way user would be typing a question or completing a query, now you might want to suggest a next word, so that it could save time and so on and so forth. Uh, then the question could be a compound sentence. There could be yeah, co-reference might need to be done. The question might resolve to multiple documents, in which case you have to ask the user back saying that I have multiple relevant documents, which one are you looking for? And maybe at the end of the Q&A session summarize what the user was interested to ask, things like that. But nevertheless, the fundamental capability that system needs to have is, given a unambiguous question, is it possible to retrieve the answer? Remember the word retrieve. So we are not going to develop a system that requires reasoning. That's altogether a different model. So one might wonder, what are its applications? Where could such system be applicable or deployed? Imagine a case where you have lots of policy documents, say related to insurance, related to healthcare, or it could be a set of legal documents. So the user could be interested in how much do I need to pay for insuring, let's say, both my parents as well as my children. How much does it cost? That could be the question, or it could be a question about. So do you have a flight from point A to point B? So depending on the domain, it might need to resolve to a particular underneath the textual documents where the answer is supposed to be present. Okay, so or it could be the situation could be a user generates a ticket. The ticket could be, I have a problem with network issue. What should I do? So in this case, network is a context, and specifically, having a problem, very low speeds could be a problem. So how do you resolve it? So in some sense, there could be a historical database against which the tickets are tagged or tied with an action policy or an action document. So now in future, given a question, can you point back to the same document to resolve that particular ticket without the help of, let's say, manual intervention? Okay. Now there could be many different applications, but nevertheless they might require different customization and tuning. Okay. So then, in the larger scheme of things, to solve this particular problem, obviously we need to begin with some data. So we are going to take squad data. Now squad is it's a curated data set where you have approximately 500 passages and more than 11,000 questions. So there is a paragraph, there is a question corresponding to that paragraph, and the answer is a selection from within the paragraph. Now that's an annotated data set we'll be working with. Um, in this case, there is no structural information present. But if you are working with some other documents, let's say a Word document or a Wikipedia actual document, there could be a lot of structural information present, such as the title, whether whether the font is bold or not, whether it's a 40 point or 12 point, and how it is basically organized. Is there a reference section available to it? So it might be organized according to the topics. So there is a lot of structural information that could provide a lot of cues, but we are not going to use that in this project. So typically speaking, it's a very high level overview of what would a chart session would look like. So there is a user is going to talk to the system. The system responds back to the agent, to the user, saying that yeah, I could answer your question. If not, it could ask a follow-up questions. So it might and correspondingly the user might continue the conversation, either clarifying with clarifying the follow-up question or simply asking a different question. So that's going to be the overall flow of the system, and this has to be realized in terms of some sort of a state machine. But nevertheless, we have to look at a fundamental piece. Now, given a question, what kind of response can be given back to the user? Okay, so that's what we are going to look at in a single Q&A system. So here is basically the question. Then we have an autofill module which is going to complete, which is going to come up with the suggestions for the next word, something like a sentence completion. The user can accept the suggestion or he can just basically proceed as he wishes. And finally, that question comes back to the text retrieval document. The text retrieval documents hits the corpus and looks at the annotated corpus, comes up with a ranked list of documents. The documents will be passed on to the answer selection module. The answer selection module, given a context in which the possible question can be resolved against, takes that particular context and highlights the answer. Basically, that's the response. That will be given back to the user. So what is different from a conventional search problem is that in a conventional search problem, typically the question is a query. Query, I mean to say, it could be a question, it could be a set of keywords, it could be a set of concepts, it could be a phrase, but it may not be a coherent sentence from a language point of view. Okay, and typically what results that you give from the retrieval in the text retrieval analysis module simply points to a document. Okay, it could be a PDF document, it could be an image, but it's not going to provide the exact answer the user is looking for. Okay, and now we're going to invert that model. When you're building a question and answer system, the question is typically longer, it could be expressed in a natural language, and the answer is going to be very short. It could be just a word. Now, for example, if you say, who is the president of India? The answer is going to be Pranab Mukherjee. It's not going to be a document, Wikipedia document that talks about Pranab Mukherjee, but it's going to be an answer. Okay, that's what we like to attempt to solve in this problem. Okay, so there are various pieces that are required to make the conversation very engaging, but the primary core features that this system needs to have are the sentence completion or autofill module. Given a question, how do you retrieve the set of context that are relevant for downstream processing? Given a document or given a passage, how do you select the answer? So these are the three pieces that we'll work with, and many other ancillary components are required to make the conversation look more engaging and look more meaningful. That requires a lot of time and probably requires a very sophisticated state space machine, which we are not going to work in this project. Let's look at the let's look at the autofill module. Conceptually speaking, basically the user comes up with a seed word. Now the seed word could be a null. That means you're going to begin from scratch, or it could be a set of 3 words, 4 words, 5 words, and the system is going to recommend the next word. The user might accept, or he could further continue with his own or her own list of words that form a sentence. Okay, so there could be several different strategies to build such models. Now we could have an n-gram based model, n-gram based next word prediction. We could use LSTMs. We could develop RNN based approaches, having LSTMs and bidirectional LSTMs. We also need to train probably our own corpus of Word2Vec based on our own corpus, maybe intersecting with Google's Word2Vec. Basically, what kind of Word2Vec embeddings we need to use. Do we need to use language features to make the sentence look more syntactically correct? So there are various components that are at play. We are going to try some of them. So the learning objectives for this particular module are we are going to use word prediction. We'll see word prediction as a natural language generation as an application of RNNs. And we'll develop n-grams as baselines, try several architectures, DNN architectures. We like to see how do we basically by doing sentence completion, how do we improve our precision and recall. This is a notable difference from a regular sentence completion problems, like a typical sentence completions that you see in sentence completions that you see in iPhone or things like that, where they're going to save time. Saving time is an objective, but that's not our primary objective. By asking more pointed questions and coercing the user to ask a question that you can answer, so that's going to be our focus. So recall that in the architecture we had a question disambiguation module. What if you could disambiguate the question by letting the user steer his question towards what is that you could answer? Then you don't need probably the question disambiguation, or you have to invoke the question disambiguation module less often. Okay, so that's going to be our focus in autofill module. Then we are going to look at the IR information retrieval module. So what we are going to develop in the IR retrieval module is we are going to develop or rather implement the existing highly optimized document retrieval scoring functions such as BM25, TFW, TF-IDF, word mover distance, and many others. So we're going to build an ensemble and a classifier which uses these features. And we are going to treat the document retrieval problem as a supervised problem. Okay, so for a given document query pair, we are going to say whether this is a positive example denoted with the +1, or it's going to be a negative example denoted with -1. In that sense, you turn so-called unsupervised problem or a ranking problem into an supervised problem, specifically as a ranking problem. So along the way, we are also going to learn a distance matrix. For example, given a document vector and given a doc2vec of the passage, given the doc2vec of the query, now you got two vector embeddings of the context and the query. Then we are going to learn the distance matrix M, using which you are going to come up with your own scoring function. And finally, that becomes another feature in the ensemble. Now, depending on the time, we are also going to try a convolution neural nets. Now, for example, we can simply treat our document as an image. For example, the sequence is basically nothing but a set of words, ordered set of words, and we have word embeddings on the y-axis. So you can see that now document is like an image. Therefore, we can apply convolutional nets on the top of word embeddings, given a set of ordered collection of words. So we might be able to learn some spatial features of the words, and they could be used as features. So we are going to see that this is like a modular architecture to learn the scoring function or ranking function. So the learning objectives from a document retrieval point of view are that so we are going to see how to use or leverage existing classical, highly optimized, highly successful IR metrics such as TF-IDF, so on and so forth. Develop modular neural network architectures. Depending on the requirement, capability, time, we could slap on different modules. And fundamentally, we are going to see the information retrieval as a supervised learning problem. And we are going to use classical machine learning algorithms like elastic regression, kernel SVM, or we could use DNNs for that matter. And the model is going to be trainable and scalable, and depending on the features that you can slap onto your DNN, it could also be used for image retrieval. Your query is an image, your document is basically a set of images that exist with you, like what you see in a Google image search. Okay. The third module we're going to work with is answer selection. So answer selection is basically given a paragraph, it's like a reading comprehension. Given a paragraph, given a question, how do you basically select an answer? Again, we are not going to generate a sentence. We are simply going to point to where could the answer be. Okay. It requires it's a very sophisticated model. We're going to use a bidirectional attention model, where a lot of features are derived and embedded into the vector space. And for example, you have words, you have characters belonging to the question, you have words and characters belonging to the paragraph. You would have a convolutional nets that derive features of basically they learn the character embeddings both for the paragraph and both for the question. And you have a bidirectional LSTMs, what are known as highway networks. This becomes your primary feature layer. On the top, you would have a context to query and query to context that basically drives the attention. For example, given a query, which part of the paragraph is going to be useful. Okay, that's going to drive. You'd have a bidirectional attention layer on the top, which basically drives the softmax. So we are going to again see this as a classification problem. The start index and end index are what going to determine your answer. In this case, the answer is basically defined as a span. Okay, suppose that you have 40 words in your passage. Now you could point to saying that answer is starts from word number 2 and ends at word number 3. So essentially word number 2 is basically your answer. So just by determining the start and end positions of the tokens of the document or a paragraph or a collection of sentences, you're pointing to the answer. So that's what we are going to work in this module. So the learning objectives in the answer selection module are, it is to learn how to read basically state-of-the-art literature, understand and reverse engineer the unstated assumption. And there'll be a lot of details missing in papers. So if you look at the code, you'll learn a lot more. And it's a pretty large project. Therefore, one would be learning how to organize code bases, how to develop commercial grade scientific software. And along the way, obviously, a lot of model specific things will be learned. For example, how character embeddings are basically done, how is basically span selection done. This is a single in multitasking. This is a multitasking problem because both we have to learn the start index as well as the end index, and both of these tasks share the same underneath hidden layer. In that sense, it's a multitask learning problem. Then, for example, if someone wants to implement Keras, what kind of APIs should be used to train a multitasking problem? So that will be the learning objectives from the Q&A system point of view. Okay, so those are the things that we'll be developing as a part of this capstone problem. Thanks for watching.